Hello. So sorry about that. Really quickly, we're just taking a vote on what we want to cover because we're not going to cover everything. So if you would like to talk about ARP, could you raise your hand again? And then you can say something in chat as well if you want. So I missed it the first time. Who raised their hand for ARP? Okay. Sure. Now DHCP.
I don't even know what
I
that
don't really
really means,
mind.
to be
All
honest.
right. I'm getting a lot of ambivalence from everyone, so we'll kind of just get into it. ARP and DHCP are very similar, so hopefully when you start to understand one, you'll understand the other. So let's just head straight into it then. Oh, here we go. I'll skip over the layer stuff because I think we chatted about it extensively in lecture. So ARP stands for the Address Resolution Protocol. It does pretty much what you'd expect it to when we are dealing with layer 3 IP addresses, so like 1.2.3.4. We have to translate this to layer 2 MAC addresses in order to actually be able to communicate. Because remember, we need to communicate on every layer. So even if we have an IP address, we still need a lower level MAC address to actually send our Ethernet frame to the right place. If we're dealing, if you remember, the internet is built on multiple LANs. So if the IP address that you're dealing with is on a different LAN, then we're actually going to send our frame to the gateway, which is going to forward it on to the right place. But it's a really simple protocol. All it really says is if you want to figure out someone's MAC address, you just shout into the network, hello, who has the IP address 1.2.3.4? And everyone who isn't that will just quietly ignore that message. Whoever does have 1.2.3.4 will respond saying, oh, the MAC address of, or the MAC address, in this case, D80, BEEF, CAFE, has the IP address 1.2.3.4. So you broadcast to everyone, and the person who actually has it will respond to you. That is the entire protocol. But are there any questions on how it works? Okay, great. So with such a simple protocol comes with such a simple protocol, we have quite a few vulnerabilities, but the main one that we'll talk about is something called ARP spoofing. So you'll notice that the protocol didn't include any checks, it didn't include any cryptographic signatures or maps or anything on it. Well, mix in this case. So the basis of an ARP spoofing attack is that anyone can respond, not just the actual person who has the IP address. So let's say you're an attacker, you want to become a man in the middle. Your victim says, hello, I want to know what the IP address of what the MAC address of 1.2.3.4 is. You're going to shoot a reply back before the actual server saying, hello, the MAC address of 1.2.3.4 is actually 66666666666. We call this a race condition because whoever gets their response back to the requester first is the one who's going to win that. So if the legitimate reply comes back first, they're going to accept that. But if my malicious reply gets back first, then they'll accept the malicious reply. This is a quick diagram of what it might look like. We have the victim who's just going to say, hello, I want to know the MAC address of 1.2.3.4, and it goes to all parties on this network. Mallory is going to say, okay, the MAC address is this malicious MAC address here, and because she was able to send the response back to the victim before the actual 1.2.3.4 on the network, then Mallory is going to win, and this response is going to be win. Questions on how this works? All right. Our defenses are somewhat simple. We have this idea of switches. Basically, say instead of actually making a broadcast request, if the switch receives a broadcast request, it's supposed to send it out on all ports. But if the switch internally knows, oh, I remember that someone asked for this 5 minutes ago, I'm just going to respond with the ARP response instead of actually broadcasting it across the network. So it limits the surface area of an attack to some extent. But really what we're going to just say for ARP and DHCP, as we'll see later, is that this is really hard to defend against. We're just going to say that the higher layers of the network are going to provide protection for us. And we're not going to try that hard in defending against ARP spoofing attack. DHCP is conceptually very, very, very similar. So this stands for Dynamic Host Configuration Protocol. As you might expect, it's a protocol for configuring hosts dynamically. Basically, when you initially connect to a network, you need to figure out, what IP address am I going to use? What's the address of the gateway? What DNS server should I use? And this is all info that you have to get from the network itself. There are a couple other aspects of it, but those are out of scope and you don't really have to worry about them too much. This is also a broadcast protocol. So when I connect to the network, I will say, hello, what configuration should I use? And all you're going to do is wait for a response that says, hello, you should use this configuration over here with this IP address, this gateway, and this DNS server. And then once you receive this, just because there can be multiple servers on the network, you're going to broadcast again. All right, I have chosen, this IP address, this gateway, and this DNS server. That's all there really is to this protocol. Any questions on this? All right. Again, because this is such a simple broadcast protocol, we have spoofing attempts. Again, because there are actual legitimate DHCP servers on the network, you're going to have to race against a legitimate response. The victim is going to ask, hello, what configuration should I use to pretend this is a DHCP server? And malware is going to say, you should use this evil configuration with, me as a man in the middle. And because hopefully you'll get, well, hopefully if you're the attacker, because hopefully you'll get to the victim before the legitimate server does. The victim is going to use our evil configuration instead of the legitimate one for the network. Defenses here are pretty much the same. Switches can mitigate this by limiting the surface area of DHCP broadcasts. And really what we're going to say is this is really difficult to defend against because there's no party that I implicitly trust on this network. So really, again, we're just going to say, we're not going to try too hard to provide security on the DHCP layer. Instead, we're going to provide security with higher layers, like TLS, which is already there. So are there questions on this? All right. In that case, let's move into question 1. Question 1 is a somewhat conceptual question about DHCP and ARP, and really just writing down what numbers you should use in order to be an attacker on the network to do spoofing and whatnot. This is a little weirdly formatted. You have question 1, then question 2, and then question 1 again, and 2, and 3, and 4. So I don't know. That's fine.
It's not the biggest problem.
Yeah. Why don't we spend 5-ish minutes working on these? I think that's it. These should be fairly simple. And then we'll come back and talk about it. Always feel free to ask, raise your hand to ask questions, either on Zoom or in person, if you want.
What did they do about assigned IP address?
Is this for question? Yeah, so remember that for DHCP, what it's doing is requesting a configuration from the network itself. So the configuration will include, you should use XYZ IP address in order to communicate. That's your assigned IP address. So they must like replace all the markers on Monday, and then by Friday afternoon, they're like all gone.
Do you need markers?
Maybe. I'm starting to consider just keeping a pack of markers myself.
Yeah. I don't think it's in any solar room we have working markers.
Which is kind of ironic, because like, if you ask the front desk, they'll just give you a pack. So,
I don't know. I didn't do this.
I
Any
don't know.
colorful ones or just black? I just have a
Um,
bunch in my
I-
backpack.
wow.
I can just have in for 50.
What's it probably black.
It also has black in it.
Blue. I do like blue.
Okay. Keep the one you like.
appreciate it. All right, how are we doing at time? Thumbs up if you're ready. Okay, I only saw like 2 thumbs up, but I'm not sure if like half of them were behind. Okay. I'm assuming people on Zoom are either not ready or just have not given a thumbs up because Zoom is hard. Okay, I've got a couple thumbs up. There we go. All right, so this is the situation we've got. You can ignore Bob for now. Let me actually zoom in on the camera. Oh, there we go. The situation we have right now, we've got us on the network, we're evil, we can call ourselves Mallory. We've got a gateway that connects to the internet, and we have Alice here who currently wants a DHCP configuration. So you'll notice Alice doesn't have an IP yet because she hasn't requested it. So now she shouts out a request, hello, I would like a configuration. Or hello, I would like an initial configuration. You know that the gateway is going to say, you know, you should use 10.10.10.77, for example, and then some other information here. But we're going to raise this gateway. What should we say in our response? Not an IP, and we have a gateway. What should we say if we wanted to be a man in the middle?
Would the IP be the same, but the gateway be like 66?
Yeah, so we're going to say, okay, the IP is 10.10.10.77 because, you know, we want to give Alice a valid thing. And we're going to say the gateway is not 10.10.10.5, but 10.10.10.66. And what's going to happen is, let's say Alice wants to communicate with Google. Alice is going to say, okay, I need to contact 10.10.10.66 in order to send a packet to Google. So Alice sends the packet, it goes to us instead of the gateway. We say, oh, that's a nice packet you've got there. I can inspect it and change it and whatnot. Then we'll probably forward it to the actual gateway who will forward it on to the internet, which goes to Google. Now, this isn't the only way we could possibly be a man in the middle. Remember, we also talked about a couple other fields that we could tamper with, right? So what is the other field that we haven't talked about that could be used to gain man in the middle power over Alex? If she wants to communicate with Google, she's at Google. Subtly backtracking here. The DNS. Okay, so if we're going to tamper with the DNS, what should we say is the IP, and then what should we do in addition to that to be a man in the middle?
What is DNS?
So this is actually covered in lecture today. So you're right that this seems a little bit out of order, but really quickly, DNS translates domain names to IP addresses. So if we said google.com is actually at 8.8.8.8, then DNS is the system that does that conversion. So if we give a phony DNS server, what would we want to do to be a man in the middle between Alice and google.com?
We want the DNS to be our own IP.
Right, so we're going to say the DNS server is really 10.10.10.6. And then when Alice asks, like, where is google.com, what should we reply with? Or what is the IP of google.com? What should we reply with? If we wanted to be a man in the middle, would we reply, say, like, oh, Google was at 8.8.8.8? Yeah, we can say, oh, you know, Google's IP address is actually 10.10.10.6. 66, you know, I'm just everyone today. And so Alice, she tries to contact Google. She sees, oh, Google is at 10.10.10.66. I'm just going to contact Google, say hi Google, and then Mallory is now in there in the middle because she can forward the packets to the real Google and then be in the middle that way.
Wait,
Question.
so when we give Alice the configuration, we set our own IP to the DNS. So what exactly is going on there? Like, so when Alice wants to contact Google, does she look at what does she look at?
So this is sort of covered in the lecture today, but basically the DNS system, you ask, hello, what is the IP address of google.com to the DNS server? So in this case, to us.
Oh, I see.
And the DNS server says google.com is at 8.8.8.8 or 10.10.10.6, depending on whether you're in motion or not.
Wait, is Alice specifically asking Mallory or is she just asking?
Alice is specifically asking whoever she thinks the DNS server. So this is usually set by DHCP. So usually we'll, if we say IP, that the gateway will say, DNS server. It should also be, let's say there's some DNS server on this network. That's 10.10.10.6. Then it would say, hello, our DNS server for your network configuration is 10.10.10.6. So what should happen is Alice asks the DNS server, hello, what's google.com? DNS server says google.com is at 8.8.8.8. And then now Alice says, okay, I'll send a packet to 8.8.8.8, which goes through the gateway out to google.com and comes back. But because we are giving a malicious DNS server, even if the gateway is valid, if we say, the DNS is us, Alice will say, okay, hello, what is google.com? Mallory says, google.com is 10.10.10.66. And then Alice says, okay, I'll contact 10.10.10.66. And then now packets that are meant for google.com are going to Mallory, who is now in the middle.
What's the gateway?
Gateway is really just your connection to the rest of the internet. So all of this, which I'm not going to try to draw a circle around, is one LAN, it's one network. And then the internet is a interconnected set of networks. All right. Now we're going to go back in time, pretend none of this ever happened. And this DNS server doesn't exist either. We are still on this network, but now Alice has received a valid configuration. So now Alice has 10.10.10.77.
Yes,
Yes. And her MAC address is 777777. Mallory is 66666. And the gateway is something else. Bob has now also joined this network. So now Bob is 10.10.10.88. He is 888888. So forth. And Alice and Bob want to communicate with each other. So Alice is going to perform an ARP request now, right? She's going to ask, hello, who has the IP address 10.10.10.88? So she shouts this to the network, and we want to be a man in the middle between Mallory, or we as Mallory want to be a man in the middle between Alice and Bob. So if Alice asks, hello, who has the MAC or who has the IP address 10.10.10.88, what should we say in our response? Like, hello, blank IP has address blank. What should we say?
IP, the contact IP, but then MAC you put your own MAC.
Right. So IP would be, do you want to give me the exact numbers?
10.10.10.88.
88, and we should say that their MAC address is what?
Mallory's MAC address, so
Which is
6666.
6666, so on and so forth. Yeah, the whole thing. And now what's gonna happen is, okay, thank you, random person on the network. Now, when I send my packet to 10.10.10.66, I think, okay, it needs to go here because that's what the MAC address is. So now the packets that are meant for Bob go to Mallory, and Mallory is now man in the middle between Alex and Bob. Now, let's say Bob is not actually on this network. Bob is actually somewhere else. So this connection is not here. Let's say Bob is just someone else on the internet. And just for correctness, let's say they're now 8.8.8.8.8. Alice is going to say, hello, who has the MAC, who has the IP address 8.8.8.8? What should Mallory say is the MAC address of that? And what should the IP in this? Okay. So actually, sure, let's go with that. 10.10.10.5. What should the MAC address be? Yeah, Mallory's MAC address again. And now Alice knows, okay, I know that Bob is outside of our network. So I need to forward packets to the gateway. Oh, well, what's the gateway's IP? Let's figure that out. Oh, I got a response saying the gateway's MAC address. Oh, I'm sorry. What's the gateway's MAC address? Oh, I got a response that their MAC address is this one. So they're expecting to forward their packets to Mallory, who will forward them on the internet to Bob.
Quick question.
Yes.
If there isn't like a man in the middle, if it's just like a regular like operation, so the gateway would know Bob's MAC address, although it's not in the same.
So it's not that the gateway would know about Bob's MAC address, it's that the gateway would know how to forward the packet along towards the direction of Bob. So Bob is on like his own network, and we don't care about his MAC address, we actually just care about forwarding it via IP. You can imagine, there are a bunch of different nodes here. The gateway doesn't know Bob's MAC address, but I know, oh, I need to forward it here. This node is, oh, I need to forward it there, I need to forward it there, I need to forward it there. If this is like some other gateway, then it'll say, oh, I know who Bob is. Bob's MAC address is 888. I'll forward the packet to Bob him. But all the gateway cares about is I'm just going to forward it somewhere closer on the internet. Yeah. There's one possible answer. The other way, and this is actually how things used to work, is that the clients, so Alice and Bob don't actually know what IP addresses are on the network. They just know that they send an ARP request and the gateway recognizes, oh, this is actually outside the network. So the gateway would send, the IP of 8.8.8.8, or the MAC address of 8.8.8.8 is actually me. Let's say this is 5. So they would basically pretend to be 8.8.8.8, and so they forward their packets on, they get the response back, and then forward them back to Alice. That's two ways that you could do this. So you could actually say, 8.8.8.8 is also 6666666, and that's how you would do it if you're working with an older network. It really depends on the configuration, but most of the time nowadays we are dealing with the clients are aware of what's outside the network, and so they would ask for the gateway. Yes.
One thing I don't understand is like you said the gateway like forwards it closer to Bob, like how does it know what is close to?
Yeah, that has to do with the BGP protocol that we talked about in lecture. It's basically, let's say we have some interconnected set of nodes. Like that. If we know, basically all of these nodes implicitly trust each other, and they will say, like, hello, I am the autonomous system for all addresses ending in 8. Hello, I am the system for all addresses ending in 7. Like, hello, I handle 101.5. And then these say, okay, this is a broadcast protocol. So this node over here would say, I know how to get to 7 by going this route. And it broadcasts that. So now imagine you're this node over here. I want to get a packet to 7. Oh, I should pretend this is working on this. It'll say, what I've heard most recently is that this node has said that they're 1 hop away from 7. So I am choosing to forward it to here, and then this node says, oh, I have a direct link to 7, so I'll forward this node. If you are, say, this node over here, you know that this node at some point broadcasted, hello, I am 2 hops away from 7. And this node also broadcasted, hello, I am, okay, this node is 2 hops away from 7, this node is 1 hop away from 7. So I choose to forward it down this way. This node says, oh, I know I'm directly connected to 7, so I forward it that way. So there's all kind of a process of like, hello, this is my fastest route. Oh, that's your fastest route. Okay, then this is my fastest route. And it's all like everyone talking to each other until you arrive at the steady state of everyone knows which way to forward it to get to a certain network. It's kind of messy and security-wise really complicated. But yeah, that's the BGP protocol summarized in too many words. Does that make sense? Yeah. All right. I think we can skip over the defenses, and then do we want to talk about? Are you interested in talking about network switches, or would you rather talk about WPA? No preference. Okay. I'd rather talk about WPA because it's an interesting cryptographic protocol. So let's hop into that. And then, of course, the answers are on the website of the protocol.
I can solve it.
Oh, are they? Fascinating. I don't handle it.
When I downloaded, I just saw that there
Oh, I
was a
see.
link.
I don't handle
didn't know-
the posting for that, so I'm not entirely sure. Sure. All right. WPA, this stands for Wi-Fi Protected Access, which is kind of a generic name. It protects your access to Wi-Fi. Computer scientists are very uncreative. There are 2 versions. Well, okay, there's a 3rd version now that we actually talked about in lecture. But WPA, the original one, uses insecure ciphers. WPA 2, we really just updated to say, okay, now let's use AES instead of some random stream cipher that we're using before. The goal of WPA is that we want to protect the link between a client and the access point. Let's say, okay, I'm going to go over here. This is my phone. It still has an home button because it's old, apparently. There's some access point up here that is connected to the rest of the network. And I want to communicate via Wi-Fi. So there's this link that we're using, and I want to protect this link against eavesdroppers. So what we need is to agree on a symmetric shared key, which we're going to call the PTK, to secure this channel. So using encryption and maps and all that. To have a secret key, we need some sort of starting secret material. It's almost like in the project, we have the password, and that's our starting secret material to protect our data from the adversary. So in WPA PSK, we have a pre-shared key, PSK, which is the password, and this is our starting material. In WPA Enterprise, what we're going to say is, oh, there's actually some authentication server sitting here on the network, which boxes, I don't know. We're going to communicate. We have a implicit channel here that we can use to authenticate ourselves, and then the access point and the server also have its own channel. And then once you've authenticated, the server will give both you and the access point a one-time secret to use as part of the handshake. So in PSK, the secret is just the password. In Enterprise, the secret is just something that you've gotten from the authentication server. From the secret, we need to do an actual handshake to have some more security guarantees. And that's what we're going to go into now. So we have our client here, our access point here, and then this is the client, and this is the over here. We start by saying, hello, I would like to authenticate. And the goal of this handshake is to prove that you know the secret material without actually leaking that secret material at all. So we're going to want some kind of randomness, some kind of replay defense, I guess, replay resistance against network attacker. So we're going to include some nonsense. The AP is just going to start by deriving some, or by generating some nonce and sending it to the client. So this is the access point nonce, the A nonce. The client is now going to generate its own nonce. So you see we have nonces coming from both sides. And the PTK is going to come as a combination of the secret and the two nonces. Now that the client knows the PTK, it can send a nonce, which it just generated, as well as a MIC, which is a cryptographic MAC, but MAC addresses are already a thing, so we have to call them MICs instead. It stands for message integrity code, which is just a message authentication code, except with different letters. It's going to send the nonce that it chose, as well as a MIC. The AP says, okay, I can verify that this MIC was generated from the S nonce after I derived the PTK. So the AP knows the A nonce, it just received the S nonce, and it already knows the secret. So it's going to derive the PTK itself, and then rederive the MIC and make sure it matches. Once you verified that the client MIC matches what you're expecting, you know, okay, I know that the client knows our shared secret. And the AP is going to say, okay, to prove myself, I'm going to send a MIC generated over some empty packet, as well as a GTK. The only purpose of this GTK is for broadcast communication. So if there's like a bunch of devices on the network, you can send one message and then all of these devices know what the GTK is. So you don't have to send one message for each client on the network. It's just one GTK that everyone knows.
Quick question.
Yes.
What do you have to check matching?
So this is just a cryptographic map, right? So to verify a map, you rederive it yourself and verify that it matches the map that was attached, right?
Oh, nice.
So MICs are the same thing, because they are the same thing. The client sends the S nonce, and then this is all encased in a packet over which a MIC is generated. Being able to generate that MIC proves that you know the PTK, which proves that you knew the secret.
Why doesn't the A nonce need a MIC?
Hmm?
Why doesn't the A nonce need a MIC?
Well, it's more like you can't generate the MIC for the A nonce, because both the AP and the client need to have some part in generating a random one-time value. So at this point, the AP doesn't know what the S nonce is yet, because the client hasn't generated it yet. And also, there's kind of a thing here where we want the client to prove itself before the AP proves itself, just because the client is the untrusted party in this case. Does that answer your question? All right. All right. So there are attacks on this, because of course there are. You'll notice that the only thing you need to be an AP here is to know the secret. Because once you have the secret, you can derive the PTK and become an access point. So we have what's called rogue AP attacks. Anyone who knows the PSK can pretend to be an access point, and that'll let you be a man in the middle. This is also vulnerable to offline brute force attacks, because once you know the A nonce, the S nonce, and whatever the MIC values are supposed to be, then you can say, okay, I will try secret equals 0, no, that didn't work, secret equals 1, no, that didn't work, secret equals 2, no, that didn't work, so on and so forth. And that's something you can do offline, so you're not rate limited by the access point kind of thing. So those are the main vulnerabilities introduced by WPA PSK. Notice that WPA Enterprise solves both of these. It solves the first one because the access point and the authentication server the access point has to be authenticated to the authentication server. So if you're a rogue malicious access point, you're not authenticated to the server, and the server doesn't recognize you, so you're never going to be able to complete the initial part of the secret distribution. And it solves the offline brute force attack Because mainly because the secret that's distributed by this authentication server is a either 128-bit or 256-bit key, which you're never going to brute force, even if it's offline. And then this channels encrypted so that they can't just see what secret that the authentication server broadcasts to the AP in the file. I think that's it. All right. Okay, we have 7 minutes left. So why don't we get into question 2, and then we're not going to get to question 3 or 4, unfortunately. What is this? So we'll spend, this one is more of an exam style question because we actually pulled it from one of the more recent exams. So I'll give, let's say 4 minutes to get as far as possible, and then we'll speed through it as fast as we can. I know it's totally not enough time, but I do want to be able to cover it before we end for today. Everyone get a fire races, by the way? The field of correction, the MAC addresses of both the client and the entry are also used to calculate the PTK. That's just to have additional defense against replay and whatnot. All right, it is, oh shoot, it's like 20 seconds to class. All right. I'm just gonna blaze through these. I'll see if I make it to the end. Really quickly, the PSK for the client, because we're using the WPA PSK, this is from the password. This is achieved by the user literally typing the password into their phone or their laptop or whatever, and the client is able to drive the PSK. For the AP, this is done during setup. So the access point knows what the Wi-Fi password is implicitly because you have to set up the Wi-Fi in order to actually do it. In order to do a brute force for the Wi-Fi password, remember that we need, for the PTK, we need the secret data, the max, and the nonces. The secret data in this case is the PSK. So we don't, yes. So in this case, she needs to know. Yeah. In this case, she needs to know the A knots, she needs to know the S knots. She's trying to find the PTK, or trying to find the PSK. The solutions say you need the PTK, but I actually disagree with this somewhat. Yeah, no, you shouldn't. Yeah, you don't need the PTK, and you're brute forcing the PSK. So I would say the answers here are actually just A knots, S knots, the MAC addresses, and the mix. That is different from the solutions, so I'm going to ping the TAs about it, but yeah, I'm not sure. If you wanted to be a man in the middle and trick someone into thinking she's the access point by being a rogue AP, then in that case, you are going to need the PSK in order to actually do that. And you also need to know the name of the Wi-Fi network, so that should be fairly intuitive. After you brute force the Wi-Fi password, you can, well, they basically do most things here. If you're part of the network, you're already an on-path attacker, so that's true. You can decrypt traffic if you know the, if a user joins after you, because at that point you can record their conversation and you know the PSK, so you can derive their PTK and decrypt their conversations. You also know the GTK, so you can decrypt any broadcast traffic, but you can't decrypt TLS traffic, because that's a completely different scheme that we only recently talked about. And that's not covered by the WPA. To defend against this, what you really, the only thing that you can do is use WPA to enterprise, just because passwords don't have enough entropy. And we haven't talked about NIDs, so we're not going to talk about that as for secrecy, in this case, I'm sorry, I know I'm rushing because we're like far over time. But WPA Enterprise does offer forward secrecy because the secret that you're using in this PTK is going to change every time we authenticate. And we're going to delete that secret once we're done, and that secret is something that the attacker needs in order to actually derive the PTK. So once we delete it, we can no longer ever derive this PTK, so we can no longer ever decrypt what was ever sent, and just therefore it's right. So sorry if those last couple minutes didn't make any sense. Feel free to chat with me afterwards about material. And I'm also going to say afterwards to chat about the enrollment. budgeting crisis that people are complaining about. So yeah, thanks everyone for coming out. Sorry, it was a bit of a rush. But we had a lot of content, and I'll see you next week.
Quick question. So the PSK is something that the client